This is how a small airplane works, taking as an example the most popular single-engine aircraft of all time, the Cessna 172. Welcome to Joyplanes. A standard airplane is composed of the fuselage, the wings, the empennage, the landing gear, and the power plant. But there are a lot more components involved. Let's start with the internal structure of the airplane, the skeleton that underpins the shape of the aircraft. The fuselage structure is made out of aluminum formers, bulkheads, longerons, and stringers. The main landing gear requires to be made out of flexible steel to withstand the forces during hard landings. If we look inside the wings, we'll find ribs, which provide the airfoil shape of the wing. Spars running through the entire length of the wings accomplish great strength, and stringers to support the shape of the wing even more. The key point here is that the shape of the airfoil is very specific to preserve the flight characteristics of the aircraft and to produce lift efficiently and with the least aerodynamic drag possible. The entire structure is covered with aluminum sheets riveted to the skeleton. This outer skin will further increase the strength of the airframe. This is called the airframe, which is considered to be the entire structure minus the engine and avionics. The green color of the skeleton structure, sometimes yellow, comes from a primer layer of zinc chromate or zinc phosphorate. It is applied to prevent corrosion on the aluminum surfaces in most parts. Older models might not have this layer of primer and will have the original aluminum metallic look. This particular aircraft has wing struts to reinforce the joint between the wings and the fuselage. It attaches from the main spar to the lower front section of the fuselage. Because this aircraft has a high wing configuration and headroom space in the cockpit is limited, the full main spars cannot go through the cockpit, and instead there are a couple of spar carry-through channels that join the two wings together. Of course, these channels are not as strong as the main spars, but that's when the wing struts come into play to distribute the load and forces. On the exterior of the airframe, we'll see the static wicks or static dischargers attached to the sharpest points of the aircraft like the trailing edge of the wings. They discharge accumulated static electricity back to the surrounding air while in flight. Without them, the static electricity builds up and accumulates on other sharp extremities, like the antennas, causing radio interference. Power plant. The power plant includes the engine, propeller, and other components. Different Cessna 172 models can use different types of engines, all of them very similar. In this model, we're looking at the Lycoming IO360. A 4-cylinder horizontally opposed piston engine that produces up to 225 horsepower. The engine not only rotates the propeller to generate thrust, it also moves the alternator to produce electricity, a vacuum pump to maintain gyroscopic instruments working, and we can also use the heat produced by the engine to keep a comfortable temperature inside the cockpit. This is also a 4-stroke engine, which means that each piston completes a cycle of intake, compression, combustion, and exhaust every 2 revolutions. At any given time, each of the cylinders in the engine is in a different stroke, meaning that there is always one cylinder in the combustion stroke, providing continuous power. The propeller is attached directly to the crankshaft, so that the power is directly transmitted from the engine to the propeller without any gear reduction. This is also known as direct drive. The propeller in this case is a fixed-pitch propeller. It doesn't require as much maintenance and it's easy and cheap to replace. Like in many aviation engines, this engine is cooled by air, taking air from the openings on the nose of the aircraft and redirecting it through the heat-dissipating structure of the cylinders, or fins. Of course, the engine needs fuel to work, and there are 2 different systems to deliver the fuel to the engine: carburetor and fuel injection systems. The Lycoming IO360 uses fuel injection, which is a more modern system with advantages over carburetors. The carburetor, in the other hand, can still be used in piston engine aircraft, but it's an older system and relies more on mechanics than electronics. The goal of both systems is to provide a mix of air and fuel to the cylinders during the intake stroke. The carburetor mixes the fuel and air before it enters the cylinder. The amount of fuel that enters the engine depends on the amount of air that is passing through it, thanks to the Venturi effect, which generates a lower pressure that sucks the fuel from the discharge nozzle. The fuel injection system is more complicated but more efficient. It uses more components and relies on electronic sensors to function well. It also needs to maintain fuel pressure in the system. It constantly monitors the amount of air and throttle setting to calculate the precise amount of fuel that has to be injected at the correct time. The injectors are located at the cylinder heads and the fuel is not mixed with air until it is injected into the cylinder. To ignite the fuel mixture, each cylinder has 2 spark plugs. It uses 2 for efficient combustion and also redundancy. The spark plugs generate a quick electric discharge powered by the magnetos. There are 2 magnetos also for redundancy, and they rotate thanks to the engine. These magnetos are independent from the electric system of the airplane. This is so that in case of an electric failure, the engine can still run. The engine is mounted on a metal frame with some elastomeric mounts to minimize vibrations. This assembly is attached to the main frame of the airplane. Fuel system. The Cessna 172 has a fuel tank on each wing. Each tank can store up to 28 gallons for a total of 56 gallons or 211 liters, but only 53 gallons or 200 liters are usable. The fuel used in this aircraft is the 100 low lead grade aviation, which is blue in color. 100 grade can also be used, in which case it's green. To refuel the aircraft, first the operator must connect the grounding wire to the aircraft. The connection can be made at the exhaust or the tie-down ring under the wing, and then the available steps will help reach the top of the wings for refueling. The fuel is distributed from the tanks through fuel lines that lead to a fuel selector switch in the cockpit. With this switch we can choose to draw the fuels from both tanks, the left tank or the right tank. This can be used to balance the aircraft if there is one tank with more fuel than the other. There is a small fuel reservoir to catch the fuel from a return line from the engine. An electric auxiliary fuel pump is used to prime the engine during startup. Then the fuel goes through a filter called the gascolator. And finally, an engine-driven fuel pump takes over during normal operation. The fuel tanks have a small vent under the left wing, and it provides a pathway for the outside atmospheric pressure to stabilize with the pressure inside the tanks. During flight, the incoming air will create a positive pressure to facilitate the flow of fuel. Excess fuel can also drip from this vent. Control surfaces. The control surfaces are used to maneuver the aircraft. The primary control surfaces that you'll find in all airplanes are the ailerons, the elevator, and the rudder. The secondary control surfaces are the flaps. Some aircraft will have more than one type of secondary control surfaces, but in most small airplanes, the flaps are enough. Let's go over the control surfaces in detail one by one. The ailerons are on the wings. They control the roll of the airplane. When an aileron moves in one direction, the other moves in the opposite direction. This generates a difference of lift on the wings, more lift on one wing and a downforce on the other, rolling the aircraft to the desired direction. The ailerons are controlled by wires connected to the main control hub, where the yokes are also connected, which, similar to a steering wheel of a car, will move the ailerons and in turn the airplane to the desired direction. This control moves the aircraft in the longitudinal axis. The elevator is attached to the horizontal stabilizer and the rudder to the vertical stabilizer. Like the ailerons, they pivot under hinges. The elevator uses the same mechanisms of wires to be controlled from the yokes. The wires run all the way back to the empennage where they are linked to the elevator. This is what controls the pitch attitude of the plane, to go up or down. To control it, you push or pull the yoke. If you push on it, that will lower the elevator, pitching the aircraft down. And if you pull on it, the opposite happens. This control moves the aircraft around its lateral axis. The elevator has an extra control, which is the trim tab. This is used to fine-tune the elevator during different phases of flight, and it counteracts the force the pilot has to use to constantly push or pull to maintain the aircraft's attitude. During takeoff, it must be centered, or as the manufacturers recommend for the aircraft. It is controlled with a vertical wheel from the inside of the cockpit. The rudder is controlled with the pedals, to go to the left or right. This motion is called yaw. The yaw rotation happens in the vertical axis. It is very important to maintain a coordinated flight, especially during turns. During flight, the airplane uses all three control surfaces to make constant adjustments if needed and to do any of the maneuvers. For example, to turn left, the ailerons have to roll the airplane left. At the same time, the pilot has to apply a bit of left rudder to compensate for adverse yaw and keep a coordinated turn. On top of that, the pilot must begin applying the right amount of elevator to make the airplane turn as well as to maintain the same altitude. The flaps are used to slow down the aircraft and generate more lift at lower speeds. They effectively increase the camber of the wings. These devices are mostly used during takeoff and landings. They can be controlled from the cockpit with a lever switch, and they are electrically actuated. Flaps can only go down, as opposed to the ailerons that move up and down. They can lower in steps of 10, 20, and 30 degrees. Flaps can only be used in a safe range of speeds. Exceeding the recommended speed for safe use can compromise the structural integrity of the flap mechanisms and the entire wing. The safe speed at which the flaps can be operated in their different configurations is indicated in the primary flight display or in the airspeed indicator with the white arc. It's important to know that the primary control surfaces work more efficiently above certain speed. At lower speeds, they lose control authority. Furthermore, at very low speeds, the airplane can enter a stall. Landing gear. This aircraft has a tricycle type landing gear, and it is fixed, meaning that the pilot won't have to worry about it during takeoff and landing. This simplifies the construction and maintenance of this airplane. The downside to this is the added parasite drag during flight, which accumulatively will make the airplane consume a small percentage of more fuel. To minimize the parasite drag, the wheels can have aerodynamic pants or fairings, and the main legs also have a streamlined shape, but some owners will remove the wheel pants to facilitate maintenance of the wheels. The drag difference can be considered negligible, but the use of wheel pants certainly improves aerodynamic efficiency. The front wheel is controlled by the pedals to steer on the ground. The pedals mechanism is connected with push rods. The wheel also has a shock absorber for suspension, and another dampener on the side called the shimmy damper to avoid oscillations on its vertical axis at high speeds on the ground. The back wheels have brakes that can be actuated independently by using the pedals. This can help control the direction on the ground and of course slow down after landing. Notice how the motion for moving the rudder and braking is different. Before continuing with the rest of the systems, I just wanted to mention how challenging the making of this video was. This video took a lot of research, animation, and logical thinking. I even learned some math and Python code for the creation of some animation drivers in Blender. Something that helped me with these challenges was learning some math and programming with Brilliant, the sponsor of this video. Brilliant is a learning platform designed to be uniquely effective. Their first principles approach helps you build understanding from the ground up. Each lesson is filled with hands-on problem-solving that lets you play with concepts, a method proven to be 6 times more effective than watching lecture videos. Plus, all content of Brilliant is crafted by an award-winning team of teachers, researchers, and professionals from MIT, Caltech, Duke, Microsoft, Google, and more. I love how you can interact with the content of these lessons to really understand what's going on with visual interactions. You have thousands of lessons to choose from, customize your learning path, and develop your skills at your own pace. You can take a lesson of a few minutes a day, or finish several lessons every day if you want. My favorite courses are about programming, and I was also pleased to find that learning anything related to math was really engaging and even entertaining. Brilliant helps you build your critical thinking skills through problem solving. not memorizing. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/joyplanes or click on the link in the description. You'll also get a 20% off an annual premium subscription. Now let's continue with the cockpit. The cockpit area is where you as a pilot or a passenger will sit. The pilot sits on the left front seat. There is also an area where additional baggage can be loaded. This plane allows to carry up to 4 adults, but it's all depending on the fuel and additional baggage loaded, as well as the weather conditions. The maximum takeoff weight of this aircraft is 2,550 pounds, or 1,157 kilograms. It can only take an useful load of 878 pounds, or 398 kilograms. The cockpit is also where you'll find all the instruments and controls of the aircraft. In the instrument panel, we can see the primary flight display and the multifunction display. This plane is equipped with the avionics system Garmin G1000. Older aircraft will have gauges and needle indicators instead, but they all accomplish the same task. Here's where the pilot finds crucial flight data such as altitude, airspeed, attitude, and engine gauges, as well as GPS location. This information is the primary reference for safe flying. One of the advantages of the digital system is that it can be configured to show the information you need in a convenient manner. The PFD shows the airspeed, altitude, attitude, heading, radio frequencies, vertical speed, and some other information, while the MFD will display the engine's RPM, oil pressure and temperature, cylinder's temperature, and of course available fuel and other important gauges. On the big area you can display the current GPS location or other navigation charts. At the bottom there are 3 analog gauges for redundancy, should both of the screens fail in mid-flight, or an electric malfunction of some kind. These are the airspeed indicator, attitude indicator, and the altimeter. With this, the pilot should have enough information to fly and make an emergency landing safely. The airspeed is gathered from a device mounted under the left wing, called the pitot tube. The pitot tube has a small hole where the air enters and is redirected through pipes that go to both a computer and the analog gauge to display the reading. If the plane is flying in icy conditions, the heating element is activated to keep the pitot clear of ice. Reading the airspeed is extremely important. The altimeter and vertical speed readings are taken from the static pressure port located to the left side of the fuselage. If this fails for some reason, like getting clogged, a switch can open a valve to read the pressure from the inside. Since the cockpit is not pressurized, the pressure will be almost identical to the outside. The attitude indicator will show the bank and pitch angles of the aircraft in real time. The digital version shows it on the big screen and it uses an IMU, internal measuring unit. But we still have the analog one for redundancy, and it uses a rotating gyroscope, which is rotated using the vacuum pump on the engine that will keep the instrument working. If vacuum pressure is lost, the instrument displays a red mark indicating no vacuum pressure. Side slip is also indicated in the PFD, with a little trapezoidal shape under the triangle. It indicates when the airplane is making a side slip to either side. If it's not intentional by the pilot, it must be corrected with the rudder. It can be more pronounced during uncoordinated turns. The old analog version of the side slip indicator looks like this. At the top, it is common to find a redundancy analog compass. On the bottom left, we can find electric switches for lights, auxiliary fuel pump, avionics, and master electricity. At the bottom, we'll see the circuit breakers. Next to them is the ignition switch and magneto selector. The airplane always operates in the both position to use both magnetos. In the center, we have the main throttle control of the engine, and next to it is the fuel mixture control. This makes the fuel mixture richer or leaner. Depending on the altitude or air pressure, the pilot will adjust the mixture control for more efficient combustion. The flap switch has the advised safe range of operational speed when the flaps are deployed. Here, it indicates that the plane must go at 110 knots or slower to deploy the flaps at 10 degrees, and at 85 knots or less to extend them from 20 to 30 degrees. To the right, we can see two knobs to control the temperature and airflow inside the cabin. Down below, we see a fuel shut-off valve. In case of any fire, this valve should be pulled out. And again, we see the fuel selector switch and the elevator trim, which we have shown already. Lights and electric system. As we saw in the panel, the lights can be switched on and off here. Other electric systems are also controlled from here. When the engine is not running, the battery is the main source of power. An external power unit can also be attached to the system. To get the engine running, we'll first need to engage the starter. This device will start rotating the engine. It draws a massive amount of current from the battery. Such power is required to rotate the engine the first time. Once the engine starts to produce its own power from the combustion process, then the starter will retract automatically. While the engine is running, the alternator will provide the power to the aircraft and the battery will be recharged. The aircraft's visibility is paramount, especially during the night. That's why this aircraft is equipped with different lights. The beacon light can be found at the top of the vertical stabilizer. It's a red flashing light and it's turned on to alert the ground crew that the engine is about to start, and it can be switched off when the engine has stopped. The strobe lights, also known as anti-collision lights, are white flashing lights that improve the visibility of the aircraft during the night. It warns other pilots in the air of the presence of another aircraft. They can be located at the wingtips and in some models also at the back. The navigation lights, also known as position lights, are steady lights that show the position and direction of the aircraft. On the left wingtip there is a red light, on the right wingtip there is a green light, and at the back there is a white light. In different versions of the Cessna 172, this setup can be achieved in different ways, but the law requires all aircraft to meet certain standards. The landing and taxi lights in this model are located in the leading edge of the left wing. They're used to illuminate in front of the aircraft during takeoff and landing, and during taxi on the ground. Although I've tried to cover as much as possible about the Cessna 172 in this video, there are many more details I haven't mentioned. Much of what I've learned about this amazing airplane is thanks to Pilot Institute and its lead instructor Greg. With their free deep dive classes and free courses, you can start learning aviation right away. Pilot Institute has collaborated with the creation of this video. They have provided in-depth knowledge and even 3D models. I've also personally helped Pilot Institute develop a free virtual reality experience called Pre-Flight Simulator, in which you can interact with these machines as if you were really standing there. You can check and see all the main components and even look into the engine. In there you will see the Cessna 172, the Piper Warrior, and the Diamond DA40. It is available for free at the Meta App Lab. As I said, they have collaborated with the creation of this video, so they are not technically sponsoring this video, but in my opinion these guys are the go-to choice when it comes to pilot training and if you plan to start your pilot career. Check all of the relevant links to Pilot Institute in the description below. I hope you have enjoyed this video. Feel free to leave any of your comments about this beautiful flying machine, suggestions for future videos or corrections about this video.